This lecture will provide an introduction to anatomy and physiology. This segment, part 3 of 4, will cover the topics of homeostasis and negative and positive feedback loops. Homeostasis refers to the maintenance of a relatively stable internal environment. Homeostasis is necessary for survival. If the internal environment was not kept stable, there would be a large change and fluctuation in things such as body temperature, blood pH, ion concentrations, and so forth. A large deviation from the normal range of any one of these things would create catastrophic results in the body, including the possibilities of organ failure and even death. To prevent this, the organ systems of the human body work together to maintain homeostasis in a process known as homeostatic regulation. In homeostatic regulation, there are usually 3 components involved: a receptor, a control center, and an effector. The receptor's job is to be sensitive, to be able to detect a specific change or stimulus in its surroundings. Once a stimulus has been detected, the receptor communicates this to a control center. The control center's job is to process and integrate the information it is receiving from the receptors in order to formulate an appropriate response. Once this has been completed, the control center will communicate directions to an effector. The effector's job is to respond to the original stimulus by either opposing it or enhancing it based on the instructions from the control center. The end result of this process is to bring about necessary changes in physiological systems so that homeostasis can be maintained. Let's explore the process of homeostatic regulation in the context of room temperature. Here, a constant normal room temperature provides a stable environment, a state of homeostasis. If the temperature of the room begins to rise, the normal condition is disturbed. The receptor, in this case a thermometer, will be sensitive to the increase in temperature and relay this information to the control center, the thermostat. The thermostat will process and integrate the information and send a command to the effector, the air conditioner, to turn on. As a result, the response will oppose the original stimulus of an increased temperature by utilizing an effector that will bring about a decrease in temperature to restore homeostasis, bringing the conditions back to normal. This is an example of what is known as a negative feedback loop. Negative feedback corrects deviation outside of the normal range by bringing about a response that opposes the original stimulus. Variations from the norm that are increases are brought back down to normal levels, and vice versa. Negative feedback is the most common type of feedback mechanism in the human body. Let's consider how the human body responds to the body temperature deviating from its normal temperature of 37 degrees Celsius. When the body temperature rises to above 37.2 degrees, receptors responsible for monitoring the body's temperature will pick up on the stimulus. This information will be sent to the thermoregulatory center of the brain, the control center in this instance, where the information will be processed and integrated. A command to effectors, in this case just the smooth muscles found in blood vessel walls, and sweat glands will be sent. These commands will instruct the blood vessels to dilate, bringing the blood flow to the surface, and increase sweat gland activity. Both of these responses will bring about a lowering of body temperature. Thus, opposing the original stimulus, and homeostasis will be restored. On the flip side, when body temperature decreases below 37.6 degrees Fahrenheit, The body's temperature sensors will again act as receptors and relay the information to the thermoregulatory center of the brain. To oppose the falling temperature, the control center will send out commands to the effectors, in this case, smooth muscles in the blood vessels, skeletal muscles, and the sweat glands. The effectors will respond by causing a decrease in blood flow to the surface, shivering, and a decrease in sweating. All of these responses will promote an increase of body temperature, thus providing negative feedback that restored homeostasis. In addition to negative feedback loops, the body also utilizes positive feedback loops in some instances. Unlike negative feedback, positive feedback will reinforce or exaggerate the initial stimulus. Positive feedback loops are found in situations where a process needs to be completed quickly, such as blood clotting and childbirth. Because positive feedback builds upon the original stimulus, it needs to have a built-in off switch so that it does not get out of control. Let's examine the process of blood clotting to see how positive feedback loops work. The damage of a vessel wall results in bleeding and the disruption of homeostasis. When the wall of a blood vessel is damaged, specific chemicals are released that will trigger blood clotting to begin. These chemicals attract platelets and will start a series of chain reactions leading to the start of blood clot formation. As this process proceeds, more chemicals are released, causing the clotting to accelerate, a positive feedback loop. More clotting leads to more chemicals being released, resulting in more clotting, and so on. The positive feedback loop is turned off once the clot has completely formed and the damaged vessel has been repaired. The bleeding is stopped and homeostasis is restored. Let's review with a checkpoint. Can you explain the function of negative feedback systems? Feel free to pause this lecture while you formulate your response. Negative feedback systems maintain homeostasis by counteracting stimuli. Let's try another. Why is positive feedback helpful in blood clotting, but unsuitable for the regulation of body temperature? Blood clotting is needed to prevent too much blood loss and requires fast response, as can be provided with positive feedback. The case of accelerating the development of a blood clot is useful. If positive feedback were used to regulate body temperature, the original stimulus would be amplified or exaggerated. The result would be an increase of body temperature, and it would continue to increase as the positive feedback loop continued. This would lead to dangerously high body temperatures and would not restore homeostasis. Rather, it would make the change in the internal environment more severe and more dangerous. This is why such mechanisms use negative feedback loops as a means of control. And finally, let's try one more. What happens to the body when homeostasis breaks down? If the body is not in homeostasis, the environment of the body changes, and the organs and organ systems cannot function properly. This results in disease and can lead to possible organ damage and death.